The next presentation here is by Konstantinos Maliatsos from the University of the Aegean, and the title of the presentation is iSEE-6G, Integrated Sensing, Energy and Communications for 6G Networks, Objectives, Use Cases, Architecture, and Initial Achievements. Konstantinos, the floor is yours.
Thank you very much, Henk. Hello, everybody. As Henk said, I'm Konstantinos Maliatsos. I'm technical manager for the project iSEE-6G, which is a project that has started in phase 2 10 months ago, and we have 13 partners from 8 countries that are trying to tackle a multitude of problems. Actually, you will see. Many of them we have already discussed, so many projects, we have overlaps. Nevertheless, I think that we have something a little bit that help us, let's say, distinguish ourselves from other projects, is that we go a little bit beyond joint communication and sensing, taking into account also energy transfer and harvesting in this context through the fact that radio and energy will be around due to the operation of sensing in many cases. So this energy can be utilized from other devices to harvest it and utilize it, especially in IoT and the Internet of Everything applications. So we have defined and we start develop the radio paradigm for joint communication, computation, sensing, and power transfer. Computation in this context means that you fuse information in the MEC. You try to exploit data from multiple sources to improve positioning and sensing operations, and also energy-related functionalities. And also you offer this as a service to UEs, so UEs can gain from the knowledge that that exists in the network in order to improve its status in the network. So what we focused on, and we will mainly address in the following slides, is that our project starts from the antenna and goes up to the, let's say, application of some type. So we start from passive and active antenna solution with intelligent configuration capabilities. So we have also RISEs involved in our project. The physical layer design for optimized operation in the GCC-SP paradigm, cross-layer design schemes, and also positioning and sensing with MEC support using 6G. And all these are coming together with the inclusion of UAVs and non-terrestrial networks, and especially with the use case, or let's say the concept of aerial corridors, which we will also see in a few slides. So the objectives of the project was to measure, characterize, and the radio propagation channel. So one of the main activities is channel measurements. To design and evaluate waveforms for our paradigm, to design, fabricate, and measure antenna systems and reconfigurable surfaces, to investigate beamforming schemes. This is also a little bit conjunction with the waveform design, to investigate new framing schemes and new scheduling schemes that include all these functionalities and how this can be coordinated under the Open RAN, let's say, concept. To investigate energy efficiency in our networks, to develop a wireless edge caching scheme for the operation for let's say, this sensing as a service operation that I mentioned, to develop a MEC-enabled system for enhanced positioning and mapping, AI-enabled collaborative positioning algorithms, same approach that I heard, and I'm very happy to hear from Angeliki in the previous presentation, and to integrate new services to emergency response, to an emergency response collaborative platform. As I said, sensing as a service, mainly used for PPDR, for protection, public protection and disaster relief. So our main research axis and domains, you can see it here as a layered architecture. Well, actually, you can identify 5 strands: channel propagation, design, measurements, and fabrication; antenna design, measurement, and fabrication; physical layer, pre-coding, reforming, full duplex; system level evaluation, scheduling, and multi-user operation for JCCP; MEC, positioning, non-terrestrial network, and emergency response applications. These are the 5 strands, let's say, from bottom to the top. And this, let's say, also summarizes and how we will, let's say, take into account non-terrestrial networks and RL platforms under this context. So one of the first things that we did in our project was to define the system model. And actually, this is a very complicated figure that you may not be able to follow. This was also the case for us. So we tried to strip it down a little bit. I think that this gives you a better view of what we are planning to do. We are talking about a network that we have distributed the radio units in the ORAN paradigm. We have included RIS with possible operation in the near field or the far field. Again, some overlap with other projects here, but it is a very interesting and hot topic for us. And we have the aerial corridor, the concept of aerial corridor, which is a volume where the UAVs should operate in a structured and with a regulatory, let's say, authority checking the operation there. And so this is good for us because we can focus, let's say, our analysis and evaluations in a specific volume space in the 3D, let's say, domain. The UAVs have plenty of roles coming from base station users, even in simulations, but we won't try to fabricate that, to be honest, but RIS mounted on UAVs. And in this context, we operate for communication, for sensing, and for wireless power transfer or energy harvesting. And all these are coordinated by the heart of the system, which is the JCCSP engine at the MEC, so that tries to fuse everything and intelligently perform, let's say, some actions on the network and to improve, let's say, performance in every functionality of the ones that I mentioned. Okay, I can move forward there. I have covered many of these. In our project, we focus mainly on millimeter wave 27, 28 gigahertz. This is because actually, as you will see, we have a very ambitious experimentation plan. So we want to be able to, and we had, let's say, to find the equipment and that we can use in order to achieve these goals for testing these advanced features. So, and as in terms of sensing, active and passive sensing is considered mainly at the network part. However, in many cases, in some cases, as I said, the users or the user equipment can also participate through getting served, let's say, getting the information by the network and fuse it with its own measurements. Now, we have also developed 6 use cases during the first months of the project. So we have joint communication and sensing in a 6G cell-free environment. Open RAN, let's say that's the first thing, but you also have to take into account the possibility of using drones as radio units. Synchronization errors and synchronization problems there may be quite significant. As I said, UAV corridors give you many different capabilities to experiment, which is quite also interesting in the research that we do, and it is done in a way that is not chaotic, so you can do assumptions that otherwise you cannot do. safety enhancement, how this sensing can be used for safety enhancement and also in applications for agricultural and industrial IoT. The sensing and actually with vehicular environment and connected and cooperative autonomous mobility. As you will see, we also have a proof of concept, a large proof of concept targeting this area. And of course, energy harvesting for IoT devices taking into account, let's say, advantage of the energy that is consumed for sensing operations. As you may imagine, the problems are plenty. So we have many research questions to tackle. Actually, I guess that are close to infinity. But anyway, this figure tries to showcase that you have several metrics and KPIs that you want to take into account, several resources and ways to address these issues that you have, several problems coming from the channel, or let's say benefits coming from the channel, several functionalities that are creating trade-offs, cooperation. This all leads to a very complicated optimization problem that may also need use of learning to be able to address it. So yeah, we have done this exercise, and as you can see, the degrees of freedom for research are many. One of the things that we are currently developing is a channel measurement system. So let's say we are building a channel sounder for joint communication and sensing mainly, using software-defined radios and rubidium clocks and custom-made antennas that will help us create this 3-node sounder setup, where also we will include an aerial node for receiver operation only. However, you can see here, these 2 nodes will practically alternate transmitting and receiving, allowing us to operate in a mode that seems like a bistatic radar, or let's say quasi-monostatic, if you like, and will allow us to also take into account the backscattering channel and all this information that are missing from existing channel models in order to be able to evaluate through realistic channel models our solutions. So, okay, we have, let's say, a very elaborate plan. I don't have time to go deep in that. If anyone is interested, I will be very happy to answer any questions, because we have spent much time to check and our, let's say, requirements and how feasible are things, especially in millimeter wave frequencies. And given that we have restrictions in power or the antenna or the switching times and of course the synchronization. So currently we're trying to test that this works, and we are very pleased with the initial results. So hopefully we will be able soon to perform channel measurements, first in the control environment, and second for aerial channels in real world conditions. Now, one other work that is progressing quite fast for our project is the antenna design and the reconfigurable intelligent surface design. So in our project, we were designing, developing, fabricating, measuring antenna arrays for the terrestrial counterpart, but also for drones, and also for channel sounding operation. You may understand that channel sounding antennas should be or can be different by the operational, let's say, antennas that require many other different have many other different requirements. As I said, 27 to 28 gigahertz is the selected frequency for implementation, and these actually are real patterns. I mean, measured patterns. So let's say a type of measure. Okay, to be honest, it's generated in MATLAB, but these are, let's say, extracted from measurements from real implementations that were done during our work. And so currently, this is the antenna that it is mainly developed in our project for 4 simultaneous beams, ARP that reaches 50 dBm, dual polarized 4 to 8 RF ports, and fast switching that allow us to operate in TDD. Actually, this antenna can also be used in a full duplex mode, so simultaneous reception and transmission from different patterns, different beams. This antenna is also slightly changed in its geometry, and also we use a reflector in order to be able to change it and have a semispheric support for drone operation. So this antenna will be used to offer connectivity from the drones to the Earth and vice versa. And the results are quite sorry for that, quite promising. Hopefully, this antenna will be ready to use in 5 to 7 months. Here is the main architecture. I know that this cannot be shown very clearly because of the size, but this is the architecture for iSEE-6G. It's not an architecture that it remains, let's say, in theory, but it is something that we plan to implement and experiment on. So we're using software-defined radios to perform the tests, our tests, focusing on the cell-free architecture. So you have 3 main system blocks that are defined. We have the radio units that host the software-defined radios, the antennas, and the functionalities that allow us to reconfigure these components quite fast. We have the user equipment, so a different, let's say, module there. And we also have I will say the DU, but in the terminology by Oran, but generally it's, let's say, the MEC, or let's say the central unit that controls the radio units. And there we have the fusion and the scheduling. So it's the orchestrator of the whole experiment and evaluation process. So we also use 5G, conventional 5G in the system. So it is practically a multi-band system. So we have millimeter wave and conventional 5G. Actually, this is done in order to help us because since we do not have, let's say, the resources to implement a complete protocol. So 6G, of course, it's not defined. These are experimental waveforms. These are experimental beams and stuff like that. So we wanted to have a backup to support us for feedback, control, and exchange of and orchestration of the whole thing. So 5G, conventional 5G, is used for this purpose. So moving forward, we are going to well, actually, 2 of the 5 technical work packages have started. So we are developing right now, are in full bloom. But moving forward, we also have the physical layer designs and the MEC support, let's say, operation. So in physical layer designs, we have started also performing some performance evaluation using stochastic geometry for various setups and beamforming scenario. We have already 10 papers in our project. OTFS has also come to our, let's say, attention. You already discussed for 6G senses, but in many cases, I fully agree with the notes and the comments that were done there, so I will not spend more time there. OTFS, but also FDM conventional types of waveforms are considered. And also in the joint communication sensing with MEC support scenario, of course, we have, let's say, multitude of sources of data and sensing results, but also a conventional GNSS that can help us to actually help the network because, for example, a LiDAR for a robot may need 150 megabits per second, and with joint communication and sensing, if you can have the same performance, it's free. So that's let's say the motivation behind all things. So now we also currently defined experimentation process with verification and validation plan. We have anechoic chambers and a big one, actually two anechoic chambers. One is quite big that will allow us to also do operational tests, however, in a very controlled environment. And this is very helpful to validate that things operate as it should. We also will check in our labs with unit testing the software-defined radio developments. And also we are very lucky to have a fleet of heavy-duty drones that will help us experiment with NTN and aerial operation. So the ultimate target is two proof-of-concept experiments, two large-scale proof-of-concept experiments that will take place in IMEC facilities and Orange facilities, Orange Romania facilities. Mainly one focusing on the SICAM and how joint communication and sensing can help us in this smart highway testbed that the guys from IMEC have developed and maintain. And the second one focusing mainly on some indoor aspects, but also some the use of heavy-duty drones for sensing and power transfer. So more or less, I think I have concluded. I try to be in time. So yeah, thank you very much.
Yeah, thank you very much, Konstantinos, for the great presentation. And to be honest, the beautiful figures, and especially the one relating to the problem formulation. Just one small.
Feel free to use it. I think for if you have students that are, let's say, wondering what they want to do in the research, I think that's a good reference.
Yeah. Thank you very much. Just one small clarification. As much as I want to have the knowledge and the fame of Henk Wemers, I'm a totally different person. I'm Sharif Saleh. I'm working in the same group, but we are different persons. So please, if anyone have any questions, please post them on the Q&A button. For me, I actually have one question. So with regards to the problem formulation figure that you shown, you have a really long list of KPIs. What do you think, in your opinion, would be the highest KPIs that we need to focus on? And in addition to that, what are the different knobs, if we can say, like design knobs that we can play in order to achieve those KPIs?
So yeah, actually, to be honest, the most, in 5G and in 6G, communication KPIs have, let's say, become very, let's say, well studied and well defined and formulated. But in terms of sensing and basically the reliability of the sensing results and how this can be, let's say, utilized for autonomous operation of vehicles, or let's say for safety operations and secure operations, these KPIs have to be very clearly defined, which is not the case in many works, and are, let's say, the ones that we will have to be quite careful moving forward. And also, so synchronization things, synchronization metrics become quite relevant because this thing that where we share this knowledge around needs to be quite synchronized in picosecond level, actually. So yeah.
Perfect. Thank you very much. And please, if anyone have any further questions, you can just mail them to Konstantinos. I'm pretty sure that he would be more than happy to resolve them. Thank you, Konstantinos.
Of course. Thank you.